So there is actually a mixture of two things, randomness and transcendental dynamics. In this case, this entire dynamics. So let's start. So, okay, moment. Let's see. Let me escape for a moment. No. Okay. So I'll be speaking really about conformal measures, randomness in the context of holomorph of transcendental and entire maps. So the key concept will be conformal measures and related issues, related concepts, in particular measures that are invariant and absolutely continuous with respect to conformal measures. So let me start the story with the history. So in 1901, Henri Lebesgue established the formula that Q-dimensional Lebesgue measure of an image of a set is equal to the integral of the Jacobian, provided that the map T is smooth and restricted to the set A, it is 1-to-1. So in the case where T is a conformal map, like for example, all holomorphic maps in the complex plane, then the Lebesgue measure of the image is just the integral of the scaling factor raised to the power Q if we are in the Q-dimensional space integrated against the Lebesgue measure, the Q-dimensional Lebesgue measure. So then, in some 17 years later, Felix Hausdorff introduced the concept of Hausdorff measures, and actually we have also the formula that if we have T-dimensional Hausdorff measure, then the image under a smooth map, so differentiable at least, is the integral against the derivative dHt. So this is like a direct generalization of this somehow change of variable formula for the Lebesgue measure. So then let's jump really ahead in the future to the year 1976, where Samuel Patterson introduced really the concept of conformal measures in the context of Fuchsian groups. So he showed that if you have any Fuchsian group, then there exists, and the delta is the Poincare exponent of the group, then there exists a measure m delta such that for every element G in this group, a measure of the image is equal to the integral over EA of G prime delta d m delta. So this is really in the dynamical setting. So this was really a breakthrough paper, very similar paper of Patterson, which had big impact on the study of geometry and dynamics of Fuchsian groups, and in particular the Kleinian groups. So Dennis Sullivan, some 3 years later, generalized or extended the concept of Kleinian groups, the concept of conformal measures for Fuchsian group to the concept of Kleinian groups. So this means for groups in any dimension. And he also brought this concept in the setting of rational functions of the Riemann sphere. And then you see this last formula that the measure of image of the set A is equal to the integral over A r prime derivative of the rational function r to the power delta dm delta, where the map R, where R is a Borel set, and the map A, and the map R restricted to A, remember the map R restricted to A is 1 to 1. Okay, so this was then actually Manfred Denker and myself started to deal with conformal measures in some more general framework, actually quite general, and we published several papers. The first one is about the existence of conformal measures for some general maps. The other one gives a full description. The second one gives the full description of conformal measures for rational functions that are parabolic, that is, that do not have any critical points in the Julia set. And then in the paper with Manfred Denker on Sullivan's conformal measures, we actually showed that there exists a least exponent of a conformal measure, and it is essentially equal what is nowadays could be called the radial Julia sets. Then there are some other papers in this direction, and Manfred Denker wrote also with Stratman. This is more recently one on Patterson measure, and he also got some very general results about this with Michko-Ryuri. Okay, so in the concept of transcendental dynamics, so meromorphic functions on the from the complex plane to the Riemann sphere, or entire functions from complex plane to the complex plane, conformal measures play an important role. Maybe the first paper on the subject was due to Krzysztof Barański, who studied in 1995 tangent family, so the functions of the form lambda times tangent of z that are meromorphic, and he proved lots of results about the geometry of the Julia set using just conformal measures and the whole thermodynamic formalism. In my paper with Elina Kotus, we generalized his approach to many more transcendental functions. And in the paper with Zdunik on the finer geometry and dynamics of exponential functions, we studied also conformal measures and invariant measures. Actually, first time where you have a function which has really essential singularity. So infinity is an essential singularity for the for exponential functions. So exponential functions are of the form that you fix a number lambda, not zero, which is a complex number, and you look at the map z goes to lambda times the number e raised to the power z. So then several papers followed. In particular, in 2004, we studied with Zdunik real analysis of Hausdorff dimension, depending on how lambda varies, and show that in the hyperbolic region, this analysis is this Hausdorff dimension depends in a real analytic way. And okay, the papers with Zdunik were actually about dynamics, which is periodic. So exponential functions are periodic. And in the papers with Volker Meyer, that this one, and that one, we just went beyond periodic functions, but still having essential singularities. So then, okay, some general result. If a function f is in class Class S is the class of entire meromorphic functions that the set of singularities of the inverse function is finite. So then one can define pressure by P of t, like pointwise pressure. This is something which mimics the general approach from thermodynamic formalism, and they prove that it exists, this limit, for outside of any set of Hausdorff dimension 0. And furthermore, they prove that this P of t is equal to the hyperbolic pressure, where pressure is the supremum over all possible classical pressures, P of f of xt, that are taken over all transitive conformal invariant repellers. Repeller means basically that this is a map on which derivative or some iterate of the that are invariant and some derivative is bigger than 1. And then they established the formula that Hausdorff dimension of the radial Julia set. This is the set of points for which so a point is in the radial Julia set if you take such a point z, then there exists infinitely many numbers, positive integers n, such that if you go from z to fn of z, you take a small ball around fn of z, then there exists a holomorphic pullback under appropriate inverse branch of fn, sending fn of z back to z. So they showed that Hausdorff dimension of this set is equal to the hyperbolic dimension and is equal to h and is equal to the infimum of such number t greater than or equal to 0, where this is P of t is less than or equal to 0. So this formula is commonly referred to as Bowen's formula, and it started really with seminal work of Rufus Bowen in 1980, and such a form with the infimum of pressure, it got maybe if one of my papers with Dan Moldin, and here they really nicely extended it to the case of large classes of transcendental meromorphic functions. So under some weaker assumption, somewhat weaker, if F is in the Yeremienko-Lubitsch class B means that the set of singularities of F inverse is bounded. For class S, it meant that it is finite. For class B, it meant that it is merely bounded. The function is assumed to be tamed. So this means that if you take the iterates of singularities, then they do not fill in the whole Julia set. So this means that actually there is a space in the Julia set on which all inverse branches are of all iterates of F are really well defined. Okay, and then the same holds. So this formula and all these formulas are outside of this difference. So, prove that it can go and function at this measure of the Julia so hyperbolic means that this particular set, which was actually this set, is the cluster of the iterate of Fn of similarity is dropping from the set. So this is some hypothesis. And they also showed that it is part of this measure is entirely charged on the set of points escaping that point belongs to z belongs to I limit of f if the limit of f of the exists and is equal to infinity. And then pressure is less is greater than is equal to 0. So they also proved something more. They showed that, if f is in the class S or in the class B, as explained in the previous slide, then if the pressure is equal to 0, then there exists a T-conformal measure on the Julia set. And moreover, they were able to show how fast this measure escape to 0 when you go to infinity. Okay. And okay, let's see. This is result of Volker-Meyer and Anna Zdulnik, who proved that there exists a meromorphic function in class B, which in class B, there exists a meromorphic function in class B, which admits no conformal measure supported on the radial points. This was for a long time an open question, and they prove it, they solve it in the year 2019. So now I will be speaking about conformal measure for transcendental dynamics in greater detail that do not fit into somehow such context. So this is first deterministic case. This is with my paper with Anna Zdulnik from 2007. So we have a function f theta from C to C, which is called exponential. So f theta of z is equal to eta times e to the power z. And okay, we then worked, actually our idea then was not to work with the map itself for a good reason, because the so-called transfer operator was not well defined, but to project dynamics onto the infinite cylinder. So you have this equivalence relation that 2 points in the plane are equivalent if the difference is an integral multiple of 2 pi I. Okay, so and then Q is the quotient of C with respect to this relation. So this is an infinite cylinder. Pi is the projection map induced by this equivalence relation. And f eta then projects down, little f eta projects down to the map on the cylinder, such that defined really in that way. And here this formula does not depend on the choice of pi inverse of the branch, of the inverse image. Whichever it is, this is the same value, because f eta preserves, little f eta preserves this equivalence relation. So, okay, let me now recall again the definition of the Regge-Julia set in this context. So this consists of all points z in Q in the cylinder for which there exists a number r bigger than 0 and delta bigger than 0 and a sequence of positive integers, which I said, for which supremum of moduli of absolute values of the real values of these maps on the cylinder is finite. So that means, so first of all, we don't want the images of f and k of z to escape to infinity. And secondly, we want that these branches are really well defined. Okay, and the parameter, we distinguished some special class of exponential functions. We called the parameter eta supergrowing if there exists C, such that okay, this inequality holds. Okay. So, okay, typical example of such maps is the function if eta is equal to 1, or actually if eta is any real number greater than or equal to 1, or actually greater than 1 over e suffices. Then the functions, then all these real parameters eta greater than or equal to 1 over e satisfy the super growing condition, but the set of such parameters eta complex 1 is really much bigger. So what we then proved, maybe the following, let me list. So first of all, that Hausdorff dimension, okay, I would say this, but for all these maps, Hausdorff dimension of the Julia set of all these maps phi eta is equal to 2. This is the result of Kurt McMullen from 1989, and for many of them, like for those which we consider that the Julia set is actually equal to even the whole sphere or the whole cylinder. So this radial Julia set is special. It is really, its Hausdorff dimension is still big enough, is bigger than 1, but is smaller than 2. So it drastically differs from the entire Julia set. And also, in this dimension, we found that Hausdorff H eta, dimensional Hausdorff measure, is both positive and finite. So this is a good geometric measure, while the H-dimensional packing measure is locally infinite at each point of the set. So the Hausdorff measure is the right geometric measure. Moreover, if you look at the measure M eta, which is the normalized version of this measure, the Hausdorff measure, then this is unique H-conformal measure for H eta, as I explained at the actually beginning of the lecture. So furthermore, we proved that there exists a unique Borel probability F eta invariant measure mu eta absolutely continuous with respect to the conformal measure M eta. Okay, in fact, this measure is equivalent to M eta, although density has points, the Radon-Nikodym derivative of mu eta with respect to M eta is unbounded. And what is really interesting, what is actually also interesting, that the omega limit set under F eta of Lebesgue almost every point in Q behaves really in a peculiar way, actually coincides with the orbit of 0 under the map F eta. So, so this means that the dynamics of almost every point is really, Lebesgue is very strange. It's really much different than the dynamics on this point on this set. So this result G was first noticed, actually was proved by Mariusz and Michael Lubitsch for the case where eta is equal to 1. Okay, so now let's go to transcendental dynamics. So I will be speaking, there is lots of approaches to transcendental dynamics. They may differ from one to the other. I will be speaking, maybe the setting, the general framework or approach is like in my paper with Volker Meyer and Bartek Skorulski from 2011. And then for random dynamical systems, with Volker Meyer in 2018, okay, this is for random transcendental dynamics, but this is for random transcendental maps that are hyperbolic. Okay, that are hyperbolic and topologically hyperbolic and expanding and have also some other nice properties. But then one could, okay, we proved quite a lot of interesting results about Perron-Frobenius operator and so on and so on. But now I will be concentrated on this paper with Anna Zdunik, which is actually a random counterpart of this paper in the deterministic setting. So, okay, so to set up the framework, to set up the setting, just now take two numbers, A and B, A bigger than 1 over E, and any omega, so infinite sequence, taking values between A and B. And then, okay, for every such omega and a number n greater than or equal to 1, define this map, F omega n, like that. So this is iterating in this order, first F omega 1, F omega 2, and so on. Okay, so this is at the moment, so this sequence of such maps can be called like actually non-autonomous exponential function or iterating exponential function. Okay. And we defined for them, for such actually sequence of functions, the Julia set, the FA2 set, phi omega. So the standard definition, look at the set of points Z such that all iterates, the family of iterates is normal, and the FA2 set and the Julia set, which is the complement of the FA2 set. So Misiurewicz in 1980 proved that if you take just f of z equals e to z, then the Julia set is the whole sphere. This was conjectured already by FA2 in 1926, and Misiurewicz provided quite actually elementary proof of this result, and we actually generalized it, providing slightly somewhat different proof than Misiurewicz, that the Julia set J omega is equal to C for any choice of maps phi omega 1, phi omega 2, and so on to iterate. The Julia set is always equal to the complex plane. So now the randomness. Randomness for us is modeled by a measure preserving an ergodic invertible dynamic system theta from omega to omega, where omega fm is a complete probability measurable space. So quite often omega can be just a Bernoulli shift, but we do not restrict to such a setting. It's regional, just ergodic, and then suppose also, but if you have a measurable function theta from omega to the set of points A, this is, see, what do we choose them? It's A, B, and C. Okay, so then we find f omega to be f omega from C to C. So f omega of this of omega times e to the power z. And the dynamics of random iterates is this, but first you take omega, you look at the point theta omega, you apply this is kind of random choice of maps f omega and omega to iterate. Okay, so now what in the project is to consider and get dynamical system on the seeder. So random dates or the dynamics, which we use this quite often, but the set omega of x is on the coordinate, the map theta. So on that one, it should be f omega of x, this type of f omega 1 of x. And so now, a little about randomness. So m omega, okay, is m omega of q are all probability measures on omega cross q, the sigma algebra, and these are all measures the project under the projection to the first coordinate on the measure m. So we call these measures random measures, and the disintegration omega this one refers to the rotation omega cross q into sets omega cross q are fiber-wise random measures. And okay, and this was now the global measure is defined just that way. The formula holds that if you want to integrate to get measure of A in the Cartesian product omega cross q, you first integrate against on the fibers, take the measures on the fibers, and integrate against the measure m. Okay, so this is okay. This set MM is equipped with the topology called a narrow topology. It is generated by the actually standard basis of neighborhoods, and okay, and now we all know the concept of tightness for measures on just Polish spaces, and it here is also the same, that for every epsilon there exists number m such that if mu is in R, so the set is called tight, then the measure of such Cartesian, okay, let's see, such that mu on omega cross qm is greater than or equal, greater than or equal to 1 minus epsilon. So to speak, qm is the set of points in the cylinder for which real part is absolute value of real part is less than or equal to m. So this is like a bounded part of the cylinder. Okay, and so I formulated in this special setting, and in this setting, Crowell's Prokhorov compactness theorem says that a set AR contained in MM is tight if and only if it is relatively compact with respect to the narrow topology. So this is direct generalization of classical Prokhorov theorem to the context of random measures. Okay, so now what we call random conformal measures, coming to real dynamics. So this, okay, given we define them by showing what is the disintegration of a measure. So such a random measure nu omega and omega is said to be T-conformal if and only if there exists a measurable function lambda t from omega to the positive reals such that nu theta of f omega of A is equal to lambda t omega, okay, of omega, it should be, but we call it lambda omega, and this integral. So this is like in the same theme as I started to talk with Lebesgue, change of variable formula, and so on and so on. Okay, and okay, our first main theorem was about the existence of conformal measures. So for every t bigger than 1, there exists mu t, a random t conformal measure for the skew product map f from omega cross omega to omega cross omega. So let me talk a little bit about the proof of this theorem. Okay, so this proof was for us at least much more involved than its deterministic counterpart for several reasons. So one of them, which is at least for me notorious for random dynamics, is the difficulty to control upper and lower bounds of the measurable function lambda t from omega to this one. Okay, in the deterministic case, this lambda t of omega is just e to the power e to the pressure p of t. So this is just one number, no problem with that. Okay, here we have a function which is a priori uncontrolled, lambda t. Actually, we overcome this difficulty by starting with a good class of random measures. I will explain this in a moment. We also must carefully control the trajectories of zero, which is the singularity of all maps f theta inverse. So if you take any neighborhood of zero, then no inverse branches well defined. This you get then just only some covering map. And all points approaching these trajectories, so trajectories of zero. This is the more difficult in the random case, but we now have that the trajectory of zero for every omega in omega. Okay. So, okay, the basic tool to approach the existence on conformal measures, I think one of the basic tools, one of the several approaches is by means of transfer of Perron-Frobenius operator. In this case, is defined by that formula. Here, LT of omega z is equal to this function. So this is like standard definition of transfer operator, and G is bounded function. So, okay, let's look at this formula in a closer way. How can one parameterize the inverse images f omega inverse of z? So these are given by this formula, okay? Log of z plus 2k pi I over eta of omega, okay? And okay, where log z is the only element omega in Q. In Q is only one in the cylinder. In the complex plane would be infinitesimal. Here is this one, and f omega inverse of z is this interval, is this collection. So then LT omega g omega of z is given by such a series. Now, okay, now if we see this formula, the first formula on the slide, then you see why this t actually we chose to be bigger than 1, because, okay, if somehow, okay, this 2k pi I is never equal to z, then this series converges, because there is like harmonic series with t bigger than 1. So this is the reason where for this exponential functions, the thermodynamic formalism, in particular Perron-Frobenius operator, only works for t bigger than 1 in this context. In general, for t bigger than the order of the meromorphic function. So, however, this operator does not act on the space of continuous functions. Okay, and even more, already the image LT omega 1 is unbounded. Okay, so this unbounded function. Nevertheless, okay, we check that for each random continuous function, G, and suitably chosen family of random measures nu, the random measures as I explained, this integral is the integral over whole Q over whole cylinder is well defined, and therefore we can speak about the dual operator. Not having really well defined the LT omegas, we can speak about LT omega star just by this definition. Okay, and then the random measure is T conformal. Actually, this is not difficult to see, if and only if it is kind of a generalized fixed point of dual operator. Okay, so this is the same as this property which you see. Okay, so now what we do, suppose that we find a set P in the random measures, the disposal and define from so phi of matter point omega is LT omega star nu theta omega over LT omega nu omega 1. Now, if you do this, then you notice that if you so satisfying this formula precisely of fixed point of this phi. So okay, so look for sufficient conditions to impose on original phi is verified on P, since P into itself, then it is continuous. Phi should be compact, and then it also is fixed point, and this point is so we look for such a good set P. Okay, how we it is compact and still also compact and complex. Okay, so definition of the space P. It's really quite technical. It's a fixed T bigger than 1, and suppose that P is such that there exists free constant, such that if you look at the measure of Q omega M0, so I recall that there is a set of points for which real part of Z, for point Z, real part of Z is less than or equal to M0. So these measures are somehow supported on a compact part, bounded compact part of the on the cylinder, and on the this is the right hand side of the complement. This is the set of points Z such that real part of Z is greater than or equal to M. Then the measure escapes really fast. Okay. Really fast if M grows. So this is first condition. Then the other condition is this W eta N, that inverse branches, the measure of inverse branches is not too big, where these numbers a eta n are given by such conditions, and bk of omega are given by such formula. Okay, and this is f eta j omega star is the holomorphic branch, okay, sending this point of iterate of 0 back to 0. So this is okay, so the proposition is this: if P is the set of all measures satisfying the conditions of the above definition with appropriate and very really careful choice, the choice of M0, CM0 and CM0 must be very careful, then phi of P is contained in P. And let's see, we prove it, okay. And okay, this is not the final, okay, this set is not the final choice. Still, if you define S of L as it is here, okay, S of L, then we define P hat, still the set of measures that are in P, but still this condition holds that nu omega of LM0 is less than or equal to SL. And then, okay, we have the following proposition: P hat is not empty. Actually, this is not so difficult. We got some explicit measures in it. P hat is convex, compact with respect to the narrow topology. Phi of P is contained in P hat. In particular, phi of P hat is contained in P hat. And then, okay, having this, we can use Schroeder-Tikhonov fixed point theorem to get a fixed point of the map phi, and consequently the random conformal measure. Okay, so then we passed to invariant measures. We proved the following theorem: there exists a unique Borel probability F invariant measure. F is this global skew product map, mu t, absolutely continuous with respect to nu t, the random t conformal measure produced above, such that moreover, mt is equivalent to nu t and mu t is ergodic. Okay, invariance, F invariance in the random setting, okay, fiber-wise settings mean just this equality. Okay, it's equivalent to to global F invariance. And okay, to prove this, the existence of invariant measures, we first proved such a theorem that there exists a constant B such that if A is contained in Q, then okay, then inverse branches do not increase measures too much. Okay, they still the measures undertaking the inverse branches still are under control. And then we defined the invariant measure as a Banach limit on this sequence. And okay, we proved all these properties. Okay, this theorem. So now, okay, passing, I think I still have some time. I started a little later, so let me take some time more. So I want to speak about geometry of random Julia sets. So here we defined also radial Julia set, but in a slightly more involved way. For every fix a number n, capital N in N, and define n omega of Zn to be the set of all integers n for which such inverse branches exist, and Fn or F omega Z is, okay, has absolute modulus or absolute value of real part less than or equal to n. So then, following number theory tradition, we introduce lower density of a subset of natural numbers and upper density. And the definition of radial Julia sets is the following. So this is the set of points Z in Q in the cylinder for which a limit if n approaches infinity of lower densities of the set n omega is equal to 1. And the radial, and then the global Julia set, the global radial Julia set is just the union, disjoint union of fiber-wise random Julia sets. And we proved maybe the following thing, that if you have any invariant measure, any invariant measure that projects onto M, this measure M, then measure of the this random Julia set is full. So this set J R of R is a good dynamical set because every invariant measure charges is fully. Okay. So we also proved the following. We defined expected topological pressure as the integral of the logarithm of logarithm lambda omega t, and proved that this pressure is finite for all number bigger than 1, but it is strictly decreasing on its domain and goes and has a right asymptote, a vertical asymptote if t goes to 1. And pressure at t at 2 is less than or equal to 0. So then, having properties 1, 2, and 3, there exists a unique value t for which expected value of pressure is equal to 0. And we proved that this, that if h is this value of t, then Hausdorff dimension of every radial Julia set is equal to h. By the way, the radial Julia set such is, we know, the whole radial Julia set is the entire cylinder. And we also proved that this Hausdorff dimension is strictly between 1 and 2. And in particular, the Lebesgue measure is, two-dimensional Lebesgue measure is equal to 0. And we got also the following corollaries. The first one is the very technical. Let me maybe not talk about it, but the second one is that for almost every, for Lebesgue, for M almost every point omega in omega, there exists a set Q omega with full Lebesgue measure, such that if you take any point Z and Q omega, then the orbit, then the omega limit set of f omega n of Z is contained in the positive extended line and negative infinity. And thank you very much for your attention.